So since we kind of skipped ahead the other day to kind of go to alcohols because you're allowed this week, I do want to go back to chapter 11 and give you the official lecture there on alkenes and alkynes, or as far as we'll get here in this section here in terms of lecturing on it. So what we're going to talk about here is alkenes or alkynes. And these are, again, two different sort of functional groups. These are what are referred to as being unsaturated. And if you remember, saturated hydrocarbons are basically carbons and alkanes that basically, because they have single bonds, they have the maximum number of hydrogens that they could have. So when we do place a double bond or a triple bond into play here, as we talked about, every time you make a bond, you do sacrifice two hydrogens. So those are what is referred to as being unsaturated. Alkenes have the functional group of the carbon-carbon double bond. So it's got to at least have one carbon-carbon double bond in there, while the alkynes have carbon-carbon triple bonds. So those are the functional groups here for each of these guys. Again, sort of the functional groups for the alkanes is the carbon-carbon sort of single bond. Now, as I mentioned, they are considered unsaturated because every time we place that bond, we do lose the two hydrogens. We also lose sort of rotation around that bond. So when we do kind of lock in a double bond, it no longer is free to rotate around. So in this sort of single bonded in alkanes, there's sort of free rotation around that bond, which is technically why you can kind of draw the guy up or down to the right. It really doesn't matter in that particular case. And the same thing sort of happens here, you know, when we have a triple bond as well. They are also based off of the alkanes. So, you know, kind of the simplest one you could have is a 2-carbon guy. This would be an alkane, as it is single bonded, and that is ethane. When we, again, make that double bond, we lose two hydrogens, one on each side. And because this is an alkene, this guy is known as ethene, E-N-E, to kind of match the group name there. And if we do one more bond in there to make our triple bond, we will end up with an alkyne. And this is what is known as ethine, Y-N-E, again, matching sort of the group name here. So again, we do sort of lose those two hydrogens as we go along. And as you could probably see in sort of our conversations, you know, it is those first 10 alkanes, really important. Everybody's pretty much named off of them. And that is our relationship as we come across here. Any questions on that there? So alkenes have the carbon-carbon double bond. They have a general form of CnH2 times N. Again, here, because of that double bond, we lose those two hydrogens. The alkanes are CnH2n plus 2 in that particular case. So for the guy we got there, ethene, 2 carbons should give us 4 hydrogens, which again is what we see here. The other sort of consequence of the double bond is it doesn't, we sort of lose the, if you remember, we had sort of the zigzag shape that occurs in alkanes because of the tetrahedral geometry that's there. This guy's tetrahedral. What we end up getting here is actually 1 electron pair, 2 electron pairs, 3 electron pairs, and 3 bonds. And that is our trigonal planar geometry, which is really our triangle type geometry. So we actually get a different geometry that occurs here. It's that guy that kind of looks like a triangle sort of happening here. at that side. Actually, on both sides, you get the triangle sort of guy happening as well. So it has a bond angle closer to what we see with trigonal planar, which is 120. And again, that's different than what we see with our alkanes that have that 109.5 degrees. And again, that's what sort of gives it that zigzag sort of shape that occurs. So ethene here, important in sort of plant hormones, also breaks down cellulose in plants. So some important functions there. Our alkyne is again our triple bond, and it has a general form of CnH2n minus 2. So if we take our same two carbons, C2, 2 times 2 is 4, minus 2 is 2, which again is why we have only our 2 hydrogens that are here. The consequence here of our triple bond is we also have a different geometry that occurs when the triple bond comes into play. Much like we talked about with bonding, that would be 1 electron pair, and the triple bond would count as 2 electron pairs. And it would have 2 bonds. Each of them would count as a bond. And that means we actually get the linear geometry here when we have a triple bond that occurs basically like a straight line. So really everything sort of flattens out near that triple bond because of that linear geometry that occurs. And that gives us our bond angle of 180 degrees that occurs in a triple bond. So in addition to obviously losing hydrogens as we make our double bond or our triple bond, we actually start to see some changing in the geometry of the molecule at those points because of the double bond and triple bond. And also, like I said, we kind of lose some rotation ability at those points because if you remember, every time we make for example, a single bond is much longer and weaker than a double bond than a triple bond. And every time you make a bond, right, everybody kind of gets a little bit closer. So double bond to a triple bond. So it also kind of brings everybody closer together when you make the double bond or the triple bond than what you have in sort of a single bond situation. So if we look at these guys here, obviously we want to identify these, and we could identify these as a alkene because of the double bond. So this is line structure here. So this guy would be an alkene. This guy here would be an alkyne. Yeah. And if we were going to sort of name, for example, the top guy, remember in line structure, pretty much everywhere the line ends or kind of curves is a carbon. So if we count it, that is 1 carbon, that is 2 carbons, 3 carbons, 4 carbons, 5 carbons, 6 carbons, 7 carbons, 8 carbons in that case. And 8 carbons would be based off of octane. We do see the double bond written in there. So it goes from octane to octene. And just like alcohols that we talked about, and we do need to sort of give the location of where the double bond or the triple bond is if there is more than one option for it. And always when you're sort of numbering an alkene or alkyne, it is the double bond or the triple bond that takes the priority. So we always want to give those guys the smallest number. So going left to right, we have carbon 1, carbon 2, and carbon 3 where our double bond would be. If we went the opposite way, 1, 2, 3, 4, and 5. So again, in organic chemistry, it's all about lower numbers important. So we would want to number left to right, and our double bond here would be at carbon number 3. So this would be 3-octene. Again, the 3 is the location where the double bond starts in that chain. Any questions on that there? Now, if we come down here, this again has a triple bond, which is our alkyne. And when you do go to sort of name these guys, you do want to always make sure that when you're counting the carbons to find the longest carbon chain, that much like the OH, that it needs to be part of it, the double bond or triple bond does need to be part of the longest carbon chain. In this particular case, you can see it flattens out here. So we got a carbon and a carbon there, right, where our triple bond is. And again, it kind of flattens out in that linear shape. So that's like 2, 3, 4, 5, 6, 7, and 8 carbons. I think that's going to be our longest. If we went 1, 2, 3, 4, and then down 5, 6, 7 on the little hook. So that looks like it is our longest continuous carbon chain. I think I counted 8 there, 2, 4, 6, 8. Again, also going to be based off of octane, but here we do have a triple bond. So it becomes octyne, Y-N-E at the end. Location of that triple bond would be at carbon number 1 right there at the beginning, right? That's probably the lowest you could get, calling that guy carbon number 1. That means that this would be carbon 2, carbon 3, and carbon 4, where we have this group hanging off of it, which has 1 carbon, 2 carbons, and 3 carbons, right? Which would be a propyl group, right? Off of those 3 carbons. And that is off of carbon number 4. So this would be something like 4 propyl, 1 octyne, Y-N-E. Question on those names. So as we'll see here in just a second, kind of jumped ahead a little bit here in terms of naming, but triple bond takes the priority and it determines which way you should number for anything else that's attached. And much like we talked about with the alcohols, once you sort of lock in whichever way you need to number for the double bond or triple bond to get the smallest number, all the other groups need to be numbered accordingly based off of whichever way you decided to go to do that. Any questions on that there? So that's just a slide early, I guess. So naming our alkanes, alkenes, and alkynes, again, they all go back to those alkanes. We still want to look for the longest continuous carbon chain. Again, must contain the double bond or triple bond in it. That will give you the base of the name, which will either end in E-N-E if it's a double bond, Y-N-E if it's a triple bond. We want to give the number of the double bond or triple bond where there is basically more than one option. That occurs approximately kind of around 4-ish carbons is sort of where you kind of need to start giving some numbers, 3 or 4 carbons. If we have a cycloalkene that has like a double bond in it, like this guy, we still would name it the same way. Again, the big shape there is basically cyclohexane, but since it has a double bond, this would become cyclohexene, E-N-E. Again, it is different than cyclohexane, which has no double bonds. And also different than our other guy there that we saw as well, which is benzene, which actually has 3 double bonds in it, are sometimes just drawn with the circle in it. So these are all 3 different things. Same idea here. We really don't need to give the location of where that double bond is in this guy because it is assumed to basically be carbon number 1 wherever it's at. If you did have something attached in addition to that, you would need to obviously use it to go whichever way gives you the smallest. So for example, if I had a chlorine attached there, we would want to call this actually 1, 2, 3 chloral cyclohexene. And we would get 3 by calling this carbon number 1. This would be carbon number 2 and carbon number 3. Now there is sort of an important rule when you have like a double bond in a ring type structure, which is when you go to number, you actually have to go through the double bond. So when you're numbering, you have to go through the double bond. And that is why you might be asking, can't we just get a smaller number by like starting this guy at carbon number 1 and this guy at carbon number 2? And the problem with that is as we go this way, we did not go through the double bond. So you actually have to go through the double bond when you're numbering, which means really when you look at it, you have basically two options in terms of the numbering. Just erase here. We'll just super zoom in on that part. So one option would be to call this guy carbon 1, and then you go through the double bond to carbon 2 and so forth. The other option would be to start here at carbon 1 and go the opposite way through the double bond to carbon 2 and so forth. So when there is a double bond in sort of a ring structure, you do have to go through the double bond when you're numbering to do it properly. And in this case, going clockwise will give us a smaller number. If we had to go the other way, this would be carbon 1, that would be carbon 2, carbon 3, carbon 4, carbon 5, and obviously carbon 6, which would be a much obviously larger number by going that way. So that's one important rule, double bond in a ring. If you start to number, either side of the double bond could be carbon number 1, but to go to carbon number 2, you actually have to go through the double bond one way or the other. And then that's the proper way of sort of numbering it. Any questions on that there? Okay. All right, so why don't we try some of these here? Take a second and name each of these guys. While we're at it, why don't we draw some stuff? Let's draw 5-methyl 2-hexene. And let's do 3-chloral 2-pentine. Let's try that there. Look for our longest continuous carbon chain and super zoom. There we go. And remember that we do want to make sure it obviously does include the double bond or triple bond. So here we have a double bond. So I think just maybe going straight across here will work. 1, 2, 3, 4, and 5. The other option would be you could start obviously here, 1, 2, 3, 4, and then go down for 5 as well. They both obviously will work. So 5 carbons, kind of put a box around it here, is based off of pentane. We do have a double bond, so that is going to be pentene, E-N-E. We do need to give the location of the double bond. And again, we have two options. We could number left to right there. So that would be carbon 1, carbon 2, carbon 3, carbon 4, and carbon 5. The other option is to go right to left, which would be 1, 2, 3, 4, and 5. The way I should go again is to give the double bond the smaller number, which it starts at carbon number 2 going left to right. So we would want a number in this direction here. Any questions on that there? So I'll get rid of these numbers here. Oh, I'll get rid of the box too. There we go. All right. Okay, so since we got that all numbered up, I'll put our box back. That should be 2-pentene. That does leave us one group just hanging out there, which is just a line. Remember, just a line and line structure. Nothing at the end of it is a carbon that should have 3 hydrogens, which is a methyl group. So that is just a methyl group. Remember, in line structure, if they do want something there, they would write it if it's not a methyl group. So if it's just a blank line to nothing at the end, should be a methyl group. That obviously we do need to stick with the same numbering. So that's going to be at carbon number 4. So that should give us something like 4-methyl 2-pentene. Any questions on that name there? Okay. Let's then go to the guy below it. This guy has, looks like 1, 2, 3, should be a carbon at the end of the triple bond, one more on the other side, and maybe one more right there. Again, you can kind of see it straightens out. So that is 1, 2, 3, 4, 5, 6 carbons, which would be hexyne, because it does have the triple bond, so YNE at the end of it. You could probably just visually see going right to left will give that triple bond the smaller number. So that is 1 and 2. So it looks like 2 hexyne. Yeah, nothing else attached there. Obviously, no other groups. So that should be our guy. Any questions on any of those two? All right, so drawing, we will work backwards here. So hexene, ENE tells me it is a double bond. The hexane part of it there tells me it's 6. So I'm just gonna do our 6 carbons here. 3, 4, 5. I'll back one up this way, 6. Double bond is going to be at carbon number 2. So again, you can go either way that you're drawing. I'm gonna call this carbon number 2 and put my double bond there, which would be this guy would be carbon number 2. So that's going to take care of that. Because I call that carbon number 2, that obviously is carbon 1, carbon 2, carbon 3, and carbon 4. I have a methyl group, which is a CH3, and you could have drew it up. I'm just going to draw it down so I don't run into the writing there. At this point, there's nothing left but hydrogens. So we're going to get everybody the 4. That is going to be 3. That's going to be 2. That's going to be 1. That is going to be 1. That will be 1. And this guy would be 3 in that case. That obviously would be our condensed formula here for this guy. Any questions on that one? Coming down to the last one, which is pentine. YNE tells me triple bond. Kind of the pentane part tells me it is 5 carbons. So good place to start would be there. 1, 2, 3, 4, and 5. Once again, the 2 tells me the triple bonds at carbon number 2. So I am going to go with this guy once again being my carbon number 2. At this point, I have on the 3rd carbon a chlorine. So that should be this guy with a Cl. Once again, you could go up with that if you had room. Everything else at this point now, again, would be hydrogen. So we would do 3. We would do 2. This carbon actually has 4 bonds, way too many bonds there. So this was a really bad choice because that has too many bonds. So, you know, that happens when you're just making up names, I suppose. So why don't we fix it by making it 4? We'll move it over. 4 chloral. Happens when you make up names, I suppose, on the fly there. So let's fix our bad mistake here. Move it this way, move it that way, and we'll put this guy over here. All right, so let's move him to number 4. Sounds better. Now we're good. Now we don't have too many bonds. So we're going with 4 chloral, 2 pentine. And then, so this guy now has 4 bonds. This guy has 4 bonds, and we would just need 3 right there. It was close. There's only 1 carbon off. It's pretty close. Any questions on naming, drawing these guys? Yeah. You want to see what the line drawings look like? Okay, yeah. All right, so let me erase some room here to do it. All right, so we will we'll start with the top one there. So if we're going to do line structure, really just kind of start the same way. Just get the right amount of sort of mountain peaks or fine, you know, which would be 6. So we want 1, 2. So 1, 2, 3, 4, 5, and 1 more would make 6 in that case. And again, 2, we would do the same thing. You go left or right. So I'm going to go left again, which means I'm just going to put a little dot here, even though you don't usually do that. But that would be carbon number 1, which means right above on top there would be carbon number 2. And that's where I would want to put my double bond in there. A little squiggly there, but maybe straighten out there a little bit. There we go. So we would put our double bond right there. Try that one more time. Not sure that looked any better, but we'll do our double bond right there. And then obviously, since we started where I put the circle as number 1, number 2 would be up on top, number 3, And then number 4 would be a methyl, which would just be a line that would come straight up like that on that particular one. Now we'll do the corrected one, which will work out here for the bottom, which was again 4-chloral 2-pentyne. So once again, I would start with the 5 in a zigzag shape. It's fine. 1, 2, 3, 1, 2, 3, 4, 5. Here we would put our triple bond there at carbon number 2, which would look, you know, something like this. Even though in reality it straightens out at that point, it's okay to kind of draw it like this without the geometry of it. So I know they kind of have it straightened out, but we could do it that way. And then obviously, once again, this is carbon number 1, which means 2, 3, and 4 would be our chloral, which we would need to write the Cl in there. If we didn't write the Cl, then it would be assumed to be a methyl group. So you definitely want to put the Cl at the end of that line. So it looks something like that. Even though in reality, that sort of triple bond would technically kind of flatten out. But for our purposes, it's okay to just do the zigzag and then kind of put the bonds on, you know, at that point without sort of showing the geometry. It should be okay. Yeah. Truthfully, it doesn't. Most people kind of start from the bottom up, if that's what you're asking, rather than kind of coming down. It really doesn't matter because at some point, probably you'll end up down maybe at some point. So it doesn't really matter. But most people kind of start from the bottom and kind of do the just, I call it almost like mountain ranges, you know, kind of draw as many peaks as you need sort of in that sense. But it doesn't actually matter in that sense. No. Other questions on that? All right, so that's all those there. Perfect. So as we talked about a second ago, with our cycloalkenes that have a double bond in a ring structure, we again don't need to give the location of where it's at, but once again, we do use it to call it carbon number 1. And if we look at their example here, kind of similar, I think maybe to the one I wrote, but this is a 5-member ring, which is that has a double bond, which is where the cyclopentene comes from. Again, not needing to do 1 or anything with that, but our double bond option in terms of numbering, we have 1 or 2 ways. They went counterclockwise, which gives it 1, 2, and 3 for the methyl group that's there. And again, your other option, as we were talking about, you do need to go through the double bond. So if you want to number sort of the other way to see what the difference would be, this guy right here would actually be carbon number 1. Then you would have, again, it has to go through the double bond to carbon 2, to carbon 3, carbon 4, and carbon 5. So again, going that way, you can see you get a much larger number than obviously going the opposite way where you get 3. Once again, you cannot just decide this is carbon 1 and then I just want to go directly to that guy, because once again, you are not going through the double bond when you're numbering, so you can't do that. Even though technically you get a smaller number if you just kind of went over there, you can't do that. You got to go through that double bond, so you cannot number that way, especially when you have a double bond in a ring structure. Any questions on that? And obviously, if you had multiple groups, you would go and give everybody sort of the numbering based off of that. So why don't you give these guys a try? Name the following here: alkenes and alkynes. And why don't we draw? Let's do 3, 3 dichloral cyclopentene. Here, clearly, the entire thing is our biggest and longest continuous carbon chain. Obviously, that is a ring structure that is 6 carbons together, which is based off of cyclohexane with the double bond. This would be cyclohexene, E-N-E on that one. Any questions on that there? The second one, once again, it is the ring structure there that is our biggest longest continuous carbon chain that obviously has the double bond associated with it. In this case, it's actually a 5 sort of member ring, which means it's based off of cyclopentane with the double bond would become cyclopentene. We also have 2 groups attached here off of that, and that is obviously one right here and one right there that is attached. Those are 2 lines with nothing at the end of them, which means they are both methyl groups. So that is a methyl, and that is a methyl group. Again, that's basically a line that has a carbon and 3 hydrogens at the end of it. So that is 2 methyl groups in the same compound. That gives us a dimethyl situation occurring. We do need to give the location of each of those. So in terms of numbering, we could start here as carbon number 1 and go clockwise, which would be 2, and this would be 3. Again, your only other option in numbering would be to start here and go counterclockwise, because that will take you through the double bond. And as you could probably imagine, that is going to give you a much larger number going sort of the counterclockwise route. So we definitely would want to be numbering in this direction, which means basically we have 3, 3 dimethyl cyclopentene. And again, you do need to give the number twice, even though they're on the same carbon. And again, we do use the parentheses in between the 2 numbers, and obviously the dash between the number and the letter. Any question on either of those 2? Lastly here, cyclopentene, which would be the same sort of structure there. That is our 5-line ring. Usually most people will draw this more like a line structure, kind of like the shapes. You could literally put the double bond anywhere you like in there. So I'm just gonna go over here on the right, but really you could put it anywhere in there. Wherever you put it, again, that is going to be carbon number 1. And in your case, or our case here, you could really call that one 1, or you could go that one 1. Again, the same rule applies. You got to go through the double bond. So I'll just, for the sake of argument, call this guy number 1, which means I do need a number this way, which means that would be 2, and that would be 3. And that is where I should put my 2 chlorines, which I do need to write in. Otherwise, again, they would become methyl groups at that point. Any questions on that there? Any questions on drawing the cycloalkenes? Obviously, if you went the other way, this would be 1, this would be 2, and you would put your 2 groups on that one if you kind of went that way instead. All right, so let's talk about another type of isomer, which is sort of a consequence of double bonds, and these are trans isomers. And basically, sistertransisomers really come about because, as I mentioned earlier, once you double bond that thing up, it pretty much locks everybody into place. You really do lose that kind of free rotation that you have in a single bond around the single bonded carbon. If you ever built a model, you could take a single bond and really just flip all the groups around, and they'll just rotate kind of freely around that. If you built the model with like a double bond, usually they're like springs or something like that, and you put them in there, you no longer could just freely kind of rotate everybody around that bond. They do get locked in. The result of that is we can make a certain type of isomers, which are known as cis or trans. Cis basically means the same side of the double bond. So that means the groups that we're talking about are either located kind of above the double bond or below the double bond. And trans is the opposite. Trans is basically opposite sides of the double bond in that particular case. Hence the fingers here, I suppose. So the thumbs are our groups. Thumbs here on the same side, which would be cis. Thumbs here on opposite sides would be trans, as our fingers there would be our double bond. When you're dealing with cis or trans isomers. The only thing that you should be concerned with in sense of trying to determine cis or trans is really just to kind of locate the carbon-carbon double bond and sort of look at what's happening on each of those spots. There is a certain rules that you have to look at when you are dealing with cis or trans isomers. And the deal is when you look at the carbon-carbon double bond, basically two things has to be there. On, say, one of the carbons, actually both of the carbons, there does need to be different groups attached. So for example, on the carbon on the left, I got an A and a B. Those are two different things that are attached. On the other carbon also needs kind of two different groups attached. So that's the first thing that you have to make sure of. The two carbons each have different groups attached. When you're dealing with cis or trans, like hydrogen could even be considered a group, even though technically it's not, but in sort of a cis or trans way you can. And then the other thing that you need is between the two carbons, there must be at least one group that's the same. So on this one, there's actually A and A that's the same on opposite carbons, and B that are the same on opposite carbons. And they happen to be on the same side of the double bond. You could look at either one, and this would actually be a cis situation in this particular case. So, so if we look at this and we focus in on the double bond here, we can see that we have a chlorine here and a chlorine here that is in the same side of the double bond, and that would be the cis isomer. If we look at the same thing and sort of isolate the double bond, we see a chlorine there and a chlorine there on opposite sides of the double bond, and that would be the trans isomer in that particular case. Now, they're both really the same molecule, except the location of those groups make them isomers because that double bond locks them into place. It actually is important where that Cl is drawn. It can't just be anywhere. It kind of gets locked into either up or down because of that double bond. All right. Now, in a cis isomer, as I mentioned, we do see their groups on the same side. So here's another example. We look at our double bond. This is a methyl group and a methyl group, and they are on the same side, which is why it is cis. And if we locate our double bond on this guy, that is our methyl group above, and that is a methyl group on the bottom, opposite sides of the double bond, which would be our trans. And you sometimes will incorporate cis or trans into the name, just kind of put it in front of the proper name. And that's where we get something like cis to butene here, trans to butene. So let's take a look at some here. So take a second and decide, are they cis or trans in each of these? Okay, let's take a look. So personally, I would just focus in right there. If it helps, put a little box there. So first off, we want to make sure that each carbon, right, has different things attached to it. So if we look at the carbon on the left, this chlorine and this methyl group are different, so that's good. This chlorine and this methyl group are different, so that is good in order to have a cis or trans isomer. So it is possible here. We also need obviously some groups that are the same on opposite carbons. So obviously we have a chlorine and a chlorine that are the same, right? We also can look at the methyl groups too, if you'd like. They're also the same. Those groups are on the same side or different side? They are on the same side, so this would be a cis isomer in this particular case. Any questions on that there? Looking at this one here, carbon on the left, methyl group and bromine, different. Carbon on the right, bromine and methyl, which are different. Group that's the same on opposite carbons, again, you can look at either one, so we'll just look at the bromine. And those bromines end up being on opposite sides, right? So this would be a trans isomer. Lastly, looking down here, we got carbon and carbon, methyl and hydrogen different, hydrogen and methyl different. Group that's the same on opposite carbons here is the methyl group, which are on opposite sides, which means this guy should also be a trans isomer. Yeah. What about the one I drew? What would that one be? Would it be cis? Would it be trans? Would it be neither? It would actually be neither in this case, because it is not possible in this one because we have the double bond. And what eliminates the possibility is when we look at the carbon on the left, we have the same group. So that automatically eliminates the possibility of cis or trans in terms of isomers. You got to have those different groups on each of the carbons. So none or neither. Now, first off, any questions on the cis or trans, how to identify them? The other thing that's really important as well is sort of the naming part of it. And sometimes people maybe mess up on the name. So let me just kind of clear out some of this real quick. Okay, so if we were to name the first one, the longest continuous carbon chain is how many? Is it 2? And that is a mistake a lot of people make because they're so focused on the cis or trans, but it actually is 1, 2, 3, and 4 is the longest continuous carbon chain. So if you were to name this guy, that would be 4 carbons, which would be based off of butane with the double bond would be butene. Double bond would be located at carbon number 2, no matter which way you go, right? So that would be 2-butene. And there also is a couple groups that are attached, one at carbon number 2 and one at carbon number 3. Also, doesn't matter which way you go in that case. So the correct name of this guy would actually be 2,3-dichloryl 2-butene. And people would put cis in front of it because it's the cis isomer. So it's very important. And a lot of times people just are so focused on the kind of double carbon in the middle. Everybody just goes, hey, it's 2 is always the longest, but it's not. Same thing here. If we look at the other ones, you'll see a similar pattern. 1 carbon, 2 carbons, 3 carbons, and 4 carbons on that one as well. And same thing on the last one, 1, 2, 3, and 4. So all these guys are really, they all are really 2-butene, all of them. And again, sometimes people focus on that center part and just think it's 2 is the longest. So you still want to make sure you look at it, even though it's sort of drawn, you know, with the geometry sort of given to you. Now, if you were asked to sort of draw this guy showing cis or trans, and let's just say we had this name given to us. Personally, if we were to draw it showing the cis or trans, I would draw it just straight first. So I would do like the 2-butene, which would just be my 4 carbons, my double bond at number 2. And at number 3 and 2 there, I have a chlorine, you know, and just kind of put them in. And again, you can fill in the rest of the hydrogens like normal. And at this point, you know, I would redraw it to sort of illustrate the cis or trans part of it. So I would start with the double bond and just go, okay, chlorine up, CH3 down, and CH3 down. So sometimes it's easier if you have to draw them just to kind of draw them straight, isolate the double bond, and then kind of draw a cis. Or if I need to do trans, I could just have drawn them opposite of each other. So sometimes it's easier to kind of do it that way. Any questions on that stuff there?